Good day. In the last lecture we talked about various multiple access schemes, and one of this set of schemes in token bus and DQDB etc. were using tokens. Okay. Now we will use the we will see two other variants of it, namely token ring and FDDI. So we are going to talk about token based MAC, and specifically so there are some kind of round robin MACs. That means the chance to transmit comes to each of the station in a round robin fashion. This can be done, as I mentioned earlier, through polling or token passing. Here we will be specifically talking about token passing. So the first system that we will talk about is the token ring. All right. So as the name itself suggests that it is a ring topology, that it is a ring topology, and a token ring MAC works with a special pattern or token which is 3 bytes long. So 3 byte words of bits called token, which moves from one computer to the next. Priority indicators are placed within the token. How the priority indicators are used we will see later. So data rate may be 416 or 100 Mbps, medium may be UTP, STP or fiber. Signaling is usually differential Manchester. We mentioned this earlier, what is differential Manchester, that how you represent your zeros and ones by electrical signals or optical signals as the case may be. And the maximum frame size would be about this 4550 bytes or right up to 18.2 kilobytes. So a token ring, like a token bus, a token is passed around the ring, and within the token is an indicator sensing whether the ring as free or busy. Okay. If that token is busy, that means some frame is being communicated at that time. The token circles continuously around the ring, passing each station. Each station is required to examine this token. So if a station wishes to transmit data and the token is empty, that means the ring is free, it seizes or captures the ring by modifying the token to a start of user frame indicator, appending the data and control fields and sending the frame around the ring to the next station. So the next station now will get the token as well as the frame, which will pass on till we get to the node where the data is copied only if it is to be passed to the end user application attached to the node. That means that data is there is a destination address kind of thing. So there is a destination. So when the destination node sees that data, it knows that this is for him. So he sort of absorbs it. That means he copies it back. He makes a copy of it and sends it to the application layer in that particular node through all the other layers maybe. So we are not concerned about that at the moment, but the token and that frame continues circulating in the ring till it comes back to the sender. So when the token arrives back at the original site, the token is once again made free and placed onto the network. So you see in this scheme is such that only one frame, I mean if the ring is busy at all, then one frame is travelling along it. So it has left the source station, then it has been copied by the intermediate nodes onto that the frame as well as the token with the busy indicator over there, and then it finally comes to the end station, and at the end station that means the destination station, he makes a copy of the data for its own use and keeps on circulating this frame and the token right up to it when it comes back to the original sender. The original sender will now strip this all this data, make the token free and put it on the ring. Now somebody else, whoever wants to transmit next, he will capture the token and then send it in this fashion. So it is a very simple kind of scheme, and this is how this shared medium, namely the ring, is being shared by all these nodes attached to it. So when station wants to transmit, it has to wait for the token, then it has to seize it, and then it transmits the frame. When station seizes token and begins transmission, there is no token on the ring, so nobody else can transmit. So since nobody, so there is no contention or collision as such, because only the station which has got the token, he can transmit, so all others do not transmit. What is the expected performance of token passing? First of all, it is fair because it is going in a round robin fashion. So, it is I mean everybody will have his chance. Each computer is given in turn an opportunity to transmit even when the traffic is high. However, even if only one computer needs to transmit a message, it has to wait till the time that it receives back the token. So, until it receives the token, it cannot start transmission, so it has to wait. Again, long messages should not be allowed because otherwise one computer may hold the token for too long. Several tokens, now there is some variation of it using slotted rings where several tokens or slots are used. These may be more useful to make it more efficient because only one, if it is a very long ring and only one frame is travelling down it, so that is rather inefficient way of using the system. So what we can do is that we might allow multiple frames, that means multiple in multiple slots, so which are sort of distributed over the space. So for example, if the speed is 200 meters per microsecond of the frame, the data rate is at the rate of 10 Mbps. So at 10 Mbps, 10 bits per microsecond. So these 10 bits will span over 200 meters over the ring. So 2 kilometer ring can hold 100 bits. That is the kind of performance with a single frame. Now let us look at how the priority works in the token ring, because what we can do is that we can give differential priorities to the nodes in the network, and this is how it works. So let us go through one example. Assume a token ring has 5 stations attached to a priority ring. Station A has priority access of 1 is let us assume is the lowest priority. Station B and D have priority of 2 and station C and E have priorities of 3. So C and E have the highest priorities. Once again assume that A had already seized the ring and is transmitting data frames. The token has a bit set to indicate that the token is busy. So the token is busy, and that means because A has already put a frame in it, and so it is being sent from A. Station B receives the frame, it has data to transmit also. So let us say that all of them wants to transmit some data. So station B receives the frame, it has data to transmit, but it cannot transmit at the moment because the ring is busy. So, but it places its priority of 2 in a reservation field within the token. So it puts 2 over there in that reservation field and sends the token and the frame sent by A along to C. It then passes the token to C. Station C also determines that the ring is busy, it has data to send, so it places 3 now. So this 3 in the reservation field, thus displacing the 2 which was inserted by B. So 2 gets replaced by 3 in the reservation field, other things remain as it is still the A's frame which is moving along. Station C then passes the frame to D. D must defer, because if you remember that we had the priority of 1 to A, 2 to B and D and 3 to C and E. So it came from A to B, B put a reservation of 2, reservation and its priority of 2, then C overrode this with a priority of 3. Now D sees that there is a priority 3 who is waiting, so and D only has a priority of 2, so it has to defer, so it cannot do anything, alright. So D must defer, it cannot place its priority of 2 into the field because a priority of 3 is already there. Consequently, it passes the frame to E, which examines the reservation field. Upon seeing the 3 in the field, it does nothing because since its priority is also 3. So E also has a priority of 3, so E cannot do anything. So E simply sends it along. Station A receives the frame back. it then makes the ring free by resetting the token and passing the token to B. B is not allowed to use the token because the reservation field inside the token is equal to 3, one higher than the priority of B. Okay. So, B cannot, although B wants to transmit and the ring is free, even then B cannot really start transmitting because somebody with a priority 3 is waiting. Okay. C is allowed to seize the token because the priority field in the token says 3 and C has a priority of 3. So, this is which means that C is the first node with that level of priority to have which has got the token. So, this sort of seizes the token, it places the data on the ring and sends the transmission to D. Now, D is now allowed to place its priority of 2, although C is sending, but C has already put his frame and D sees that now naturally the reservation field is reset. Now, D can place its priority of 2 into the reservation field, it does so and passes the frame to E. E of course also wants to send. So, E displaces D's priority of 2 with its priority of 3 and passes the frame to A. A also wants to send again, but A must defer any reservation placement since its priority is 1. B must also forego any priority allocation since its priority is 2. C receives its transmission back, it is required to make the ring free, it does so and transmits the token to D. D is not allowed to seize the ring since its priority of 2 is less than the reserve priority which has been put there by C, reserve priority indicator of 3. So, it passes the token to E. E seizes the ring because its priority of 3 equal to or greater than the reservation of 3. So, this is the way the priority ring works. If you see that whoever put the reservation earlier, somehow I mean it at the same level, so it comes back to him, so he puts the frame over there. So, but if the higher priority nodes have finished reservation transmission etc., then the lower priority nodes can start transmitting and so on. So, you can set these priority levels in the token. So, this is how not only you can have a pure simple round robin where everybody has the same priority, or you can have priority based token ring also. Okay. There is a variation of this dedicated token ring which is called dedicated token ring, where there is a central hub. So, here this is a more centralized system which acts like a switch, and it is more like a full duplex point to point link, and concentrator acts as frame level repeater and no token passing. So, we will pass this. Next, we will take up another system. This system called FDDI. This is still in use in some places where some specific applications, but then again FDDI is also sort of going out because other newer technology is taking its place. Okay. FDDI was originally conceived as a high speed network, and this network could be I mean FDDI could be used in a LAN, and it is used in a LAN. It is also used in the WAN or in the backbone as high speed data, because when it was conceived at that time 100 megabits per second was considered to be very high speed. Of course, things technology have changed, but still it is instructive to look at these technologies, first of all to see that how different MAC schemes can work, and new MAC schemes for new technology etc., they are also coming up all the time. So, we will just as an instructive thing we will look into FDDI in some detail. So, FDDI was conceived as a high speed backbone technology. It is a dual ring topology, just like your maybe your, if you remember your SONET rings, and we talked about dual ring topologies when we in optical networks. By the way, this is based on fiber. So, this is fiber distributed data interface, that is the acronym FDDI is for fiber distributed data interface. So, it uses dual ring topology using fiber optic cable used to transmit light pulses. Optical fiber channel operates at a rate of 100 Mbps. Well, we can say 100 Mbps only at today, but then at one point of time when it was sort of the standard was proposed in early 80s, it was supposed to be very high speed. Frequently used in LANs to connect buildings together. So, ring circumference can extend to 200 kilometers. Distance between nodes can be up to 200 kilometers. Okay. So, FDDI network can host up to 1000 nodes on one optical fiber. That is how it was conceived. Of course, this optical fiber is not just one continuous optical fiber. This optical fiber goes from by hop, that means from node to the node. What kind of nodes, etc., that we will see. So, this is just an FDDI topology, just like we have two rings. Sorry. A is known as the primary ring, so which is shown in blue, which is shown in black. The primary ring is the one which usually carries all the data, and then there is a secondary ring which is used for fault tolerance purpose. Okay. As a matter of fact, this is one reason why FDDI was used and is still used in some places where the reliability of the network is of a very high concern, and we want to get the the network, we cannot allow it to remain down for any length of time. So, FDDI can quickly switch from the primary to the secondary ring. So, there is a protection kind of system, as you can see, because there is one ring which is wholly dedicated as a secondary ring which is there. So, in case of a fault either of a link or in a particular node, we can quickly have another ring in its place. So, the FDDI standard specification, which as I said came up in 80s. So, this has various parts. One is the media access control part, MAC. So, how medium is accessed, the frame format, token handling, addressing, and error recovery. All right. Actually, FDDI has a somewhat more complex MAC protocol, because FDDI allows both synchronous as well as asynchronous traffic. All right. Now, if some traffic is synchronous, that means if it is carrying some kind of let us say voice or something, then you know that this 125 microsecond length is very sacred and sacrosanct over there. So, every 125 microsecond some channel may have to send something. All right. So, that is there, as well as we can have packets or data flowing in the network, maybe with some kind of a lower priority. So, this can handle a mixture of both synchronous and asynchronous traffic. That is a peculiarity of FDDI system, which makes its MAC somewhat more complex than a plain vanilla token ring. So, we will see this a bit of details of this MAC later on. The physical layer protocol defines the data encoding and decoding, how data is encoded and decoded, we will see this later, clocking requirements and framing. The physical layer medium, characteristics of transmission medium, fiber optic link, power levels, bit error rates, optical components, connectors, etc. So, that is also a part of the standard for the physical layer medium. And there is some standard says something about the station management, defines station and ring configurations, initialization, scheduling, collection of statistics, fault isolation, and recovery from faults. Okay. As I said, that recovery from faults is was and still is a very strong point of FDDI. One reason why for some application FDDI may be preferred. So, as mentioned earlier, topology of FDDI network consists of two independent rings. Primary ring A is used for data transmission, while secondary ring B provides an alternate data path. This has already been shown, and secondary ring remains idle unless primary ring fails. So, optical fiber rings are counter rotating, that means one is moving in one direction while the other is moving in the other direction. So, two signal paths are provided, one in each direction. Why do we make the rings counter rotating? Well, we had seen this in our recovery lecture also. The reason is that if there is a node failure, what you can do is that suppose there are two suppose you are a station, all right, and there are two counter rotating rings passing through you, that means one the signal will pass in this direction, in the other the signal will pass in this direction, all right. Well, and of course in optical fiber this is quite fixed, because you want to have proper transmitter on one side and the receiver on the other side. So, one ring is moving like this, the other ring is moving like this. Now, what might happen is that suppose the next station has failed, and this station understands that there is something wrong either with the link or in the with the next station. So, what it might do is that it might make a quick connection over here, so that the ring coming in this direction may take out this other path, and still we can make one ring now. Now, this ring will not have any fault tolerance, there will be one ring by using a part of the two rings A and B. So, we can get a recovery through that. So, that is why we have two counter rotating rings with two signal paths provided, one in each direction. A station may be a computer, workstation or node connected to FDDI network. So, there are some network nodes also, we will talk about this. Or a station must be connected to both in order to use the secondary ring as an alternate data path. If it is connected to only one of them, then it cannot use the alternate path. So, media is, as I said, 1300 nanometer optical fibers. Transmission method is baseband, that means there is no modulation, only the pulses in the raw form are travelling down the ring. Data rate is 100 Mbps. And topology is a physical ring of trees and a logical ring. Why ring of trees? Where did trees come from? We will talk about it. Now, let us talk about the type of network stations which may be connected to an FDDI ring. One is a dual attached station, which is connected to both the rings. That means it is a station which is connected to both the rings, that is why it is called dual attached. Then we have dual attached concentrator, DAC, which is connected to both rings and provides connection for additional stations and concentrators. It is actually the root of a tree. This is where the tree comes from. I have a picture. So, we have this. So, this is the picture of an FDDI concentrator. So, you can see that this is the main part of the concentrator, and the two rings are there, the counter rotating. This is the primary ring and this is the secondary ring. So, the primary ring is coming like this from A to B and the secondary ring is going like this. It has some additional ports from which other stations may hang, and actually what might happen is that we may have a tree hanging from a concentrator. Okay. So, we have a tree of nodes here. So, that is why this main FDDI ring may be a ring of trees. Okay. The way FDDI is actually deployed, and this is also interesting in the sense is that you may have a very large ring, that is possible. Sometimes what is done is that we make a very small ring in the core of the system, okay, like wherever your main server and other things is, we make a very small ring just within the within a room, all right. And what happens is that we have concentrators connected to this ring, and from this concentrator a tree spans out to all the other maybe nearby buildings or whatever, so that all of them are connected to this FDDI backbone, but the backbone is has got two rings. So, this backbone is fault tolerant. So, that is a good thing about FDDI. So, that is one way FDDI may be deployed. So, we have a very small ring and trees spanning out and going out of the building maybe to other buildings and so on, all right. Or alternatively, of course, you can have a large ring also. So, we have these dual attached stations and dual attached concentrators. So, concentrators could be the roots of trees. And then of course, we have of course, dual attestations and dual attest concentrators are more costly. We have a cheaper variety if you think that is good enough, which is a single attestation, which is attached only to the primary ring. Similarly, you have single attest concentrators, which is connected only to the primary ring through a tree. A double attestation or concentrator can reconfigure the dual ring, as mentioned earlier, into a single ring in the event of a failure. What are the physical interfaces like? As opposed to a basic token ring network in which at any instant there is a single active ring monitor which supplies the master clock for the ring, in FDDI this approach is not suitable because of high data rates, that is one thing, and the other thing is that the ring could be very large. So, if the ring is quite large, then you have having the central clock becomes difficult. So, FDDI approach, so each concentrator would have on each ring interface has its own local clock, and the outgoing data is transmitted using this clock. All data to be transmitted is encoded, as I mentioned earlier how it is encoded prior to transmission using a 4 of 5 group code. So, which means that there are really 32 possibilities. So, for 4 bits of data we have actually 5 bits which are going over there. So, the additional capacity is used in some other way for control purpose that we will see later. This means that for each 4 bits of data a corresponding 5 bit code word or symbol is generated by the encoder. Some of these symbols or combinations are used for link control functions. Now, let us go through the ring operation, which is there are 2 aspects to it. One aspect is similar to the token ring which we have already discussed. So, sending station waits for a token, sending station captures and strips token and then transmits frames, sending station issues token at the end of transmission. Now, this is one point where this FDDI is different from a token ring. In a token ring, if you remember that only when the transmitted frame with that busy ring etc. comes all the way back to the sender, that is when the sender makes this token free and puts it back on the ring. Okay. Since FDDI was perceived as a high speed ring, so what was proposed was that as soon as its transmission of its frame is over, it can put a new token on the ring. So, multiple frames may be circulating in the ring at the same time, okay, bringing up the speed. So, sending station issues token at the end of transmission. Destination station copies the transmitted frame and sets the A and C, which is the address recognized and frame copied indicators. That means it has already copied the frame, just somewhat like what we have in token ring. Sending station removes the data from the ring by stripping the sent and acknowledged frame etc. So, it takes out the frame. The first few bytes of the frame are not stripped, this is for some technical reason, we need not go into the details here, and continue to circulate on the ring as a fragment. Each repeating station strips one byte from the fragment and a transmitting station completely strips it. So, there are some fragments also, apart from the frame, some fragments are also moving around in the ring. Now, we come to token passing scheme. Uses token passing protocol to move data around the ring, uses another protocol based on timers. Okay. So, we will look at this protocol later on. Timing is very critical to token passing scheme as it is designed for delay sensitive synchronous data. Alright. So, as I mentioned earlier, the FDDI ring carries a mixture of data. Okay. It may carry lower priority packet data kind of thing, which we have been talking about, let us say in token ring. It may also carry synchronous data, okay, which is time sensitive, so which has a somewhat higher priority than this other one, and this is based on some timing protocol, and we will go into the timing protocol now. So, FDDI allows for high data rates where each ring interface has its own clock. All outgoing data is transmitted using this clock. A node will get packets within a specified amount of time. So, this is now we are discussing the timing part of it. So, a node will get packets within a specified amount of time. As a packet circles the ring with a token behind, each station retimes and regenerates the packet. So, this increases probability frame fragments will be propagated on the ring, we need not bother about this. So, how fragments are eliminated. Early token release is required because of the high speed and extensive distance provided by FDDI. So, I mentioned this. FDDI rotation time. FDDI uses time to ensure equal access to the ring, measures rotation time by calculating distance of segments, processing time and the number of stations. So, this is the time you expect a packet to move around the entire ring. Rotation time refers to how long it takes for a signal to propagate around the ring. So, rotation time is used to control the priority operation of FDDI ring. We have several times. One is measured by a clock that times the period between the receipt of tokens, called the token rotation time. That means how long is it that the token takes to come around the ring. And the operation of MAC layer is governed by a MAC receiver and is calculated by target token rotation timer. That means there is a target token rotation timer, that means target token rotation time which is prefixed, and there is a TRT which is measured. Okay. So, this so TTRT, of course, usually you would expect that under normal condition when the load is moderate, the token rotation time would be less than the TTRT. So, that is the when the node is moderately loaded. By comparing TRT with TTRT, we can find out how loaded the system is, and depending on how loaded it is, we would of course, if we have a synchronous link going through the synchronous traffic going through this FDDI ring, then the synchronous traffic will have to be given the first priority, and the asynchronous traffic, that is some maybe some lower priority data traffic, they will be put on the ring or will not be put on the ring depending on how loaded it is. This is how it is calculated. There is a pre-negotiated target time called PTT. PTT is coordinated for the arrival of a transmission. Each node measures time it takes for the token to return to it, that is the TRT we have talked about. It compares time to a pre-negotiated target time PTT for its arrival. A node is allowed to transmit as long as its full transmission stream does not exceed the PTT. Okay. So, so there is a pre-negotiated target time which is allowed, and a node is allowed to transmit as long as its full transmission stream does not exceed the PTT. If the token comes back sooner than PTT threshold, it is deemed as a light network load. If the token comes back later than PTT, it indicates a heavy traffic load. Low priority traffic must then be deferred until load on the network becomes lighter. There is a token holding time THT. So, actually THT is equal to, if you look at the last point, THT is actually equal to TTRT minus TRT. So, what is it? It is used to calculate maximum length of time a station can hold the token to initiate asynchronous transmission. The point is that there is a target time and there is an actual measured time by which the token has come back. If the actual measured time is low, that means the network is lightly loaded. So, you can put some asynchronous traffic on that. So, that is why this THT is calculated. So, it calculates the difference between the arrival of the token and the TTRT. It keeps track of the amount of time a host can transmit. So, formula is this, and then you have the following rules. If THT is less than 0, that means traffic is heavy, the total rotation time is actually now more than the expected time which was sort of fixed or expected earlier, which means that all asynchronous traffic has to wait, the synchronous traffic will go through. So, the THT is less than 0, which is a heavily loaded stations can only transmit the synchronous traffic. If THT is greater than 0, stations can transmit both synchronous and asynchronous traffic during THT. So, it first sends the synchronous traffic and then sends the asynchronous traffic till THT falls to 0. If THT is equal to 0, host cannot start any new packet. THT increases and number of stations decreases. Now, a quick look at the FDDI frame format. We have a I mean, as a matter of fact, any kind of framing, as we will see, I mean, as I said that FDDI is a technology which is not moving forward very much these days. So, and as a matter of fact, it may be slowly on its way out, because we have other ways of achieving the main point of FDDI, which is its fault tolerance. We have other ways of achieving that. Apart from fault tolerance, of course, the speed of FDDI has become, I mean, 100 Mbps is rather I mean, considered not very fast. I mean, so far as backbone is concerned, it is taken as a very low speed these days. So, FDDI may be on its way out, and naturally it's also expensive, and the support to it is also dwindling. The reason we are sort of looking at this is how different MAC protocols, I mean, how different issues are handled by a typical MAC protocol. But anyway, this business about framing is common to all kinds of data link protocol. So, we will later on, when we talk about Ethernet, which is the most common kind of network in the world today, so we will see that it has its own frame format. And if you remember our first day's discussion, when we were talking about these different layers, that just to remind you that these different layers, they have at the same level, that means a network layer to network layer in this node to the network layer in this node. Similarly, the transmission layer in this node to the transmission layer in that node, or the etc. They have some protocol running, all right. And how do this protocol run? These protocols run by adding some header, and in some cases a trailer also to the main payload. So, whatever it gets from the upper layer is the payload. To it, for running its own protocol, it adds some header, that means adds some information to the beginning of the frame and adds some information to the end of the frame to make a complete frame, and the corresponding layer in the other node strips this particular information, does whatever it has to do, because it also is running the same protocol, so it knows what to do, and then maybe either it goes up or it goes down again to the next station, and so on. So, this is an example frame format of FDDI frame format. This has some preamble. We will not go into the details of this, because this is not very important anymore, but we will just mention that such fields are quite common in many frames. We have a start delimiter, we have a frame control, we have a destination address. This has to be there, because otherwise the station will not know that this particular packet is meant for him. We have a source address field, so we have a DA, then an SA field. We have the data, frame check sequence for some error control. By the way, error is not handled by FDDI. Error is, I mean, it allows other layers to handle the error if there is an error, but you have to check the error. So, frame check sequence, end delimiter, and frame status. Okay. And then we talked about the encoding process in FDDI. FDDI encodes all data prior to transmission, uses a 4 or 5 group code method, which was mentioned earlier. Encoder generates a corresponding 5-bit word or symbol. For every 4 bits transmitted, FDDI creates a 5-bit code. Bits provide clocking for the signal itself. The status of bit reflects a change of state of the light on the other side. So, this is what the symbols are like. 10 taken with another symbol they form 1 byte. There are 16 data symbols. With 5 bits we can have 32 different symbols, out of which 16 data symbols are reserved for data. This is for 0 to f. So, if you write your stream of bytes in hex, that means 4 in groups of 4 bit each. So, each of these 4 bits is has got its corresponding code in the FDDI symbol. So, from 0 to f, and then we have 16 other symbols which are left. So, 8 are used for control as control symbols and 8 as violation symbols. The control symbols are called Q, H, I, J, K, etc. is not important. Coding the symbols prevents occurrence of 4 consecutive zeros in a row. This is necessary to ensure each station's clock is in sync with the other station. So, the transitions that take place when you go from a 0 to a 1, that transition edge is used for synchronizing the clocks. This is a very common method of synchronization. So, that is why we have got the codes in such a manner, so that we do not have a long string of zeros, because then the synchronization may drift. Token field, the token has the following fields. So, we have a preamble, we have a start delimiter, we have a frame control, and we have an ending delimiter. So, token is a simple kind of token like this. As I said, one of the main points of FDDI is the fault tolerance that it provides. There is a ring wrap. I mentioned this earlier, that in a concentrator, in a dual attached concentrator, if it senses that on the other side the node has failed, it can make a connection between the primary and the secondary ring within itself, so that the ring, while coming like this, sort of starts traveling like this and completes it. Because if you have a node on the other side also, the corresponding concentrator will also see. So, he will also make a connection between the primary and the secondary ring. So, the failed node is essentially isolated. On both the sides there are connections within the concentrator, and instead of a single ring, you have instead of 2 rings, now the 2 primary and secondary rings have fused together, and then suppose this was the primary ring coming, then it goes back, and then the secondary ring through the secondary ring to the other concentrator on the other side, and the connection is completed. So, you have 1 ring. So, that is why the physical diameter of an FDDI ring is kept within 100 miles, so that if there is a failure, the ring diameter, total ring diameter does not exceed 200 miles, which is the standard. So, ring wrap techniques is the same technique as we mentioned earlier when we talked about protection and restoration. Technique is used to manage failures. When a station fails or a cable is damaged, dual ring is automatically wrapped. 2 adjacent ports connecting to broken link will be removed from ring, and both stations either enter wrap state. FDDI concentrator switches to wrap state and ring is doubled back onto itself. Data continues to be transmitted on FDDI single ring. Performance is not negatively impacted during wrap state. So, this is the good thing about FDDI. So, when you have very mission critical situations, so that is where FDDI when kept its strength for quite some time, and that in very critical situations like maybe say stock exchange or maybe something where even a few seconds network down is not acceptable to anybody. So, there you can you could deploy this kind of technology where with its very inherent fault tolerance. So, this is the another picture of the FDDI ring wrap as is shown over here, that you have one station 4 which has gone down. So, that 2 adjacent stations, namely 2 and 3, they wrap around, and we have a single ring now going round. Okay. So, this is clear. And how is it done? This also we have discussed earlier. That means we have optical bypass switches used for 2 or more failures to occur. Rings are segments back into 2 independent. By the way, what would happen if more failures occur? Okay, suppose there was a one single node failure, and the 2 rings, primary and secondary, then the 2 adjacent concentrators, they wrapped back, and we had a single ring like this. All right. Now, what happens if another node fails in between? So, what would happen is its adjacent concentrators would once again wrap around, but now instead of only one single ring which we had earlier in case of single failure, now with this double failure we may have 2 rings. Okay. Now, these 2 rings are not connected to each other. So, these 2 rings individually would still keep working, alright, because there is a part of the protocol which I have not covered, is that if what happens if there is a single token which was on the other side, now the token is lost, there is no token. So, there is a protocol for reclaiming a token, reclaiming and generating a token. There is a protocol for doing that. So, they will do that, and now what would happen is that 2 individual rings will come into operation on the 2 sides. They will not be able to. So, the nodes which are connected to this subring and the nodes which are connected to the other subring, they will not be able to communicate with each other across, but within themselves they will very well communicate as usual, alright. So, rings are segmented back into 2 independent rings incapable of communicating with each other. Additional failures can cause further ring segmentation. So, optical bypass switches can eliminate failed stations from ring to prevent ring segmentation. So, how is it done? Well, how is it done? We have all seen. Actually, this is all done with mirrors. So, optical bypass switch has optional optical mirrors that pass light from ring directly to a dash station during normal operation. Dash station experiences a power loss. Optical bypass switch will pass the light through itself. So, uses an internal mirror to maintain ring integrity. So, that is done. And the other technique of this protection etc., which we had seen earlier, namely dual homing, alright. This dual homing is also used, could be used in an FDDI context. A router or a dash you remember is a dual attached station, is connected to 2 concentrator ports on FDDI concentrator. One port could provide a connection to active fiber link, while the other port is in hot standby mode. Actually, there are 2 nodes A and B. Usually, the A node is in hot standby mode and the B node is operating. So, port is in hot standby or passive mode. Hot standby is constantly tested and will take over if primary link fails. So, typical dash configuration has a B port is designated as active port and the A port is configured as the hot standby. When the primary link fails, passive link automatically activates and hot standby becomes operational. So, it is the same dual homing principle which we had seen earlier when we were talking about fault protection, failure and recovery, okay, recovery and protection. Okay, with this we come to the end of our discussion about token bus, token ring and FDDI. So, we have discussed a number of these token based protocols, namely token bus, DQDB, token ring and FDDI. These are actually what has happened was this FDDI was this way was quite good, only thing was that FDDI was also quite costly. Okay, maybe not so. These technologies are actually going out in some sense. Okay, one of the technologies which is sort of derived from here, if you remember when we were talking about DQDB, we were talking, so it handled 53 byte cells. So, that sort of came down to ATM, and ATM is a technology which is still quite alive today. So, we will have an extensive discussion about ATM. Regarding the WAN technology, 2 other technologies which are once again on their way out, they are X25 and frame relay. Well, frame relay is still there in many parts, X25 is sort of going out, but still we will just have a quick look at these. And then when we have considered these MAC level, so this is how the next set of lectures will go. So what will happen is that when we finish this, then we will talk about the, we are talking, remember now we are talking about the data link layer and specifically about the MAC sublayer of the data link layer. Then we will have to talk about the LLC, that is the logical link control. So we will discuss that, and the other important functionality of this data link layer, which is the error and flow control. So how error, if there is an error, because whenever you have a transmission, somehow you have to assume that errors may occur. Okay, depending on the medium and the technology, errors may be more or less frequent. For example, in a fiber, the error may be very low, error probability may be very low. When you are using wireless, the error probability is high, but anyway you have to consider the possibility of some error. So how errors are handled, that means we are talking about now bit errors which may come in due to noise and other things into the data in a particular link, that is one thing. And if there is a flow control to be done, that means whether if there is a congestion or not, because you are sending from one side, whether the other side is receiving it or not, that you have to somehow have to make out. So these things then we will take up next. Thank you. Good day. So today we will start our discussion on data link layer. As a matter of fact, we have already discussed a part of the data link layer, namely the MAC sublayer, and we will see how that all fits in. But to fit it into the broader picture, if you remember when we were discussing the 7-layer OSI protocol, starting from the application layer, the bottommost layer was the physical layer. So we have finished our discussion on physical layer, and just above the physical layer we have the data link layer. So we will look at the different components of data link layer and how they are used, and we will look at a few protocols, etc. So that is what we will do. So our main this thing is data link protocols, which are the protocols which are used in the data link layer. Now what are the main tasks of data link layer? It transfers data from the network layer of one machine to the network layer of another machine. So actually this is the part of the service it gives to the upper layer. You remember that above the data link layer we have the network layer, alright. So below the network layer we have the data link layer. So the data link layer gives some service to the network layer, and this service is the transfer of data from one network layer to another network layer. So that is the service it gives to the network layer, and this in its turn uses the physical layer. So it converts raw bit stream of the physical layer into groups of bits, etc., or frames. So this is how we can look at it. So this is one node and this is another node. Above this, of course, there may be other layers. We are not concerned about these upper layers at the moment. So this gets some data to be sent from the network layer, and this data link layer sends it to the next data link layer. Remember once again that the network layer is concerned with transfer of data, etc., across the network. That means it may take several such hops, but data link layer is just concerned with a single hop. So this is how we simplify the problem of going multi-hop. So this multi-hop part we leave it to the network layer. For this single hop, so multi-hop naturally will constitute a number of such single hops, and data link layer would handle the transfer of data from one node to the next. So what are the kinds of services, type of services that the data link layer gives? One is unacknowledged connectionless. So no attempt to recover lost frames. If some frame is lost due to noise, error, etc., etc., there is no attempt to recover this, because and there is no acknowledgement from the other side. It is a connectionless system. suited for low error rate networks or for fault tolerant applications such as voice. What do we mean that voice is a fault tolerant application? We mean that even if some of the bits in a voice stream, digitized voice stream, that is, even if some of the bits drop, obviously there will be some degradation on the other side if you are not doing any kind of correction, etc. But to the human ear it may not be very perceptible. Okay. For example, I am talking, even if there is a momentary glitch, you would more or less make out what I am talking about, alright. So, that is why in that sense it is very inherently fault tolerant. So, that is unacknowledged connectionless service, that is one kind of service. Acknowledged connectionless service, this is another kind of service. So, each frame is acknowledged by the receiver. So, this is suited for unreliable channel where so require this acknowledgement for special reliability. Acknowledged connection oriented service ensures that all frames are received and each is received exactly once, and these services are accomplished using, as I said, simplex, not usual but half duplex or full duplex channels. So, this is some examples, not very important. Sorry. So, it is a reliable message stream. It may be connection oriented service or it may be connectionless service. It may be a reliable message stream or reliable byte stream. So, reliable message stream sequence of pages, reliable byte stream, let us say remote login. So, they are coming byte by byte. Here it is coming page by page. Unreliable connection like digital voice, unreliable datagram. So, these are, but when you come to datagram, this becomes connectionless service, unreliable datagram, acknowledged datagram, request reply, etc. Now, let us look at just one thing, that where does this all this data link layer exactly, where does it exist? Physical medium we understand, it is a cable or it is this electromagnetic field, this free space, etc., or a fiber, so we can see it, we can feel it. But where does the data link layer reside, so to say? Okay. Now, frames could be fixed length like ATM, alright. So, ATM cells are of fixed length. So, you know, once you have synchronized, you know that they are going to come with in a 53 byte kind of regularity. But frames could be variable length also, in which case we use this byte count, byte stuffing, bit stuffing, generic framing procedure, Manchester encoding, etc.